All right, it's my pleasure to welcome again Vishnu to give the next talk in our series, and he'll be telling us about estimates. Okay, Vishnu, take it away.
Thanks, Glenn. So I'm going to be doing probably the last big estimate for this series. So this estimate is kind of like, so remember that a few weeks ago I proved the gradient estimate for mean curvature flow of two convex surfaces in dimension 3 or higher, right? And so that was kind of a very kind of, I say, straightforward maximum principal calculation. You computed some auxiliary function that involves the thing you're trying to estimate, and then you compute the heat operator on that, and then you take the terms, can get rid of all the bad ones, and in the end you get some kind of estimate that you want. The argument in this this gradient estimate I'll prove today, the argument is very different. It's much more geometric, and it involves, well, I guess we do have to use the maximum principle, but it's already been done. And it involves using kind of the inscribed and exscribed radius estimates that I maybe talked a little bit about last week. So recall that we had these things called the inscribed and exscribed curvatures. So we had this function mu x, y, t, which was 2 x of xt minus x of yt times the normal vector at xt divided by the distance between x of xt and x of yt. And what I said was that this quantity, if x is a solution to mean curvature flow, or even if it's not a solution to mean curvature flow, it's just an embedding of a surface, then this quantity here is the curvature, the principal curvature of the largest ball that is tangent to the surface at x and passes through the point y, right? So that's 3 conditions, so there's a unique ball that does this. And now we can define the inscribed curvature, xt, to be the supremum over y that's not equal to x of mu x, y, t. So this quantity is the inscribed radius. Curvature. So that's the curvature, the principal curvature of the largest ball contained inside your surface. And then this one I didn't talk about last time, but this is the exscribed curvature, which is the infimum of the same quantity over points that are not equal to x on m. Sorry, this m, that's okay. Yeah, well, let me just finish writing this. X, y, t. That's the exscribed curvature. And so this is mt, where I'm writing just shorthand mt to be x of mt if I'm writing my notation as x m times 0 t is a solution to mean curvature flow. Okay. So last time what we showed was that under mean curvature flow, if our initial surface has this, if we initially have that the inscribed curvature divided by h at the initial time is bounded by a constant, then mu, the same thing, same quantity is bounded by the same constant at later times. Okay, so basically what this says is that if I have a surface that's evolving under mean curvature flow, if I have a point where if at every point I have a inscribed ball of radius, a constant divided by h, right? Then at later times, I still have that same, I have inscribed balls of the same radius, constant divided by h. Okay, so so why would one expect to be able to kind of derive gradient estimates for the curvature by looking at looking at this quantity? Well, if you have some kind of surface, it does actually give you some control over the curvature, because you're saying that there exists a ball on the inside that has some fixed radius, right? And that means that you have your surface can't be too badly curved, right? Because you're bounded between these two balls. And actually, the same thing is true for the x-scribed curvature. So you also have the same thing on the outside. So you have two-sided, you have some kind of two-sided bound on your surface, right? And that hopefully is going to give us some kind of gradient estimate, okay? All right, so now I'll state this theorem. So this theorem is due to Haslhofer-Kleiner, but there's kind of similar kind of theorems of similar flavor that I've seen earlier in mean curvature flow, where you use kind of these bounds on maybe on the interior and exterior, maybe using convexity estimate to somehow conclude some kind of curvature estimate, which then is used to prove convergence of blow-up limits or something. So suppose we have some kind of family of surfaces, MT, which I'll write as the boundary of some compact set, omega t, for t in some small parabolic neighborhood, let's say t0 minus r squared, comma t0, mean convex mean curvature flow in Rn plus 1. Now, suppose you have h at some fixed point x0, comma t0 less than or equal to r inverse at some x0 in M, t0, then, oh, sorry, I need another condition. And you also have these non-collapsing conditions, which has bounds on the inscribed curvatures. So there is some constant alpha greater than 0 such that the x-scribed curvature is bounded like this, and the inscribed curvature is also bounded similarly. Right? We have these two-sided curvature bounds. This is saying that at every point in M, there is a ball in the exterior of radius alpha divided by h. So when h is big, you expect it to be small. Yep, alpha divided by h. And this one is saying that same thing in the interior. There is a ball of radius alpha divided by h. Right? And by the previous results, we know that this is preserved along mean curvature flow. Right? And yeah, so this is true in a parabolic ball centered at x0, t0. So that means it's the ball of radius r at x0, and we have in time it's parabolic. And you know this is these kind of r squared and r is chosen so that if you rescale, then rescaling the domain, actually this scales just by scaling r. So then there exists some Cn constant, Ck greater than or equal to 0, such that the kth derivative of A supremum in P sigma R x0 t0 is less than or equal to CKR to the minus K minus 1. So there exists CK greater than 0 and sigma in 0, 1. Although I don't see where in the proof this actually implies that sigma has to be less than 1. It seems to me that sigma is actually equal to 1. But maybe, but there must be some reason why it has to be, where the sigma pops up. Okay. So let's okay. So let's assume k equals 0, right? So once we have bounds on curvature in a parabolic neighborhood, then you can use just the maximum principle to get bounds on the curvature, on the higher derivatives of curvature. But I'm not going to do that proof, but I think that's due to, I think, interior estimates of Ecker and Huisken, but you can do this from the maximum principle, just like, kind of how when we did the high derivative estimates for in n greater than or equal to 3, same thing works here. But just bounding the curvature, that's a bit more difficult. Okay, so now suppose the theorem is false. Right, so now we're trying to prove that the curvature, just the norm of A, second fundamental form, is less than or equal to CKR to the minus 1. C0R to the minus 1, right? Okay, so suppose the theorem is false. Then we can find like a sequence of mean curvature flows that have the following properties. There's a bunch of scales j greater than 0, right? So we just need to kind of find the correct statement here. So a bunch of scales r greater than 0, a sequence of properly embedded mean curvature flows mtj hat, where t is in, okay, so r greater than 0 and tj times tj, such that we have mean curvature flows like this, tj minus rj squared, tj, this is mean convex. And we have a bunch of points xj in mj tj hat, such that, so it satisfies the first condition, which was h hat j xj tj is less than or equal to rj inverse, but doesn't satisfy the second condition on the curvature. It doesn't have the curvature bound. prj xj tj a hat j is greater than or equal to, okay, so we had a greater than or equal to ckr, so there doesn't exist a constant ck such that this is true when k is 0. So that will just be j. So you can make the constant arbitrarily large in a sequence of examples. Okay, so the strategy here is, so I mean, if this theorem were to be true, then if I did any kind of rescaling like this, because the curvature is bounded, I should get in the end a flat surface, right? I've bounded curvature, I'm rescaling by something that goes to infinity, so that in the end I get something that is flat. Okay, so if I assume that that's not true, then if I rescale these sequence of examples so that A is still greater than, is still strictly bounded away from 0, I should then try to prove that that sequence converges to a static hyperplane. Okay. All right, so now I'm going to define a new sequence by rescaling this example here. So define a sequence of solutions to mean curvature flow mtj, where t is in minus j comma 0 by so the way I get mj, so we start with the surface m hat j t in tj minus rj squared comma tj. Okay, so now let's start by just doing standard kind of blow up sequence. So I get translate the points xj, tj to the space-time origin. Okay. Now, parabolically, we scale by. So I want to rescale by something that goes to infinity, but I also want to make sure that I don't also take the second fundamental form to 0 in order to get this contradiction I'm looking for. So I'm going to rescale by JRJ inverse. So the second fundamental form of this new surface, when I rescale by that, will be always greater than or equal to 1 in a parabolic ball. JRJ inverse. And I'm also going to rotate so that the normal vector of MJT hat at x0 t, xj maps to, in this, like I'm rotating, so this in this, after doing all this stuff, this translating and rescaling is equal to en plus 1. Okay, so at the origin, when I rescale, the normal vector is equal to en plus 1. So let me just maybe say what this, so then this this sequence mtj t, okay, so I'm parabolically rescaling. So let me just maybe take a look at this. Why do I get minus j comma 0? When I rescale by jrj inverse, then so firstly I'm translating xj tj to 0 0, so this tj and tj, that becomes just 0 here and minus rj squared here. Now when I rescale by jrj inverse, over here the r's will cancel because when time scales by lambda squared. So then I get a minus j here, right? So this is defined from minus j to 0. And this satisfies. So remember, I translated xj, tj to the space-time origin. So I know that the spatial origin is contained in mj0. The normal vector, which I said before, the normal vector of this thing is at 0, 0 is en plus 1. And the mean curvature. Okay, so the mean curvature is originally less than or equal to rj. So when I scale by jrj inverse, that divides by jrj inverse, the rj's cancel. So h is bounded by rj inverse. So we have this is good because now we know that h goes to 0, but on the other hand, because of this assumption here, stop E100 of aj is greater than or equal to 1. Okay, so it's not flat. Okay. Are there any questions about this part? So what I'm going to try and do here is that this sequence here, I want to prove that this actually converges to a static hyperplane, which means that it contradicts this third statement here. So let me write that down. That this sequence of mean curvature flows.
You mean the fourth statement, like the A is
right? Yeah, that one.
Yeah.
Yeah. So this thing converges smoothly to this set xn plus 1 equals 0. T. Yep.
Sounds good.
Okay, so yeah, so how do you do this? So remember that, so if I scale a surface, then it also scales the inscribed and exscribed balls that are at, if you have a point and you scale the surface, then there's also a scaled ball, like whatever the inscribed radius is at that point also gets scaled, right? So the hope is that if I have some kind of inscribed ball on the interior and the exterior, then those, when I'm taking this rescaling, then those balls are going to radius infinity, which means that the entire lower half plane is contained inside, well, is on one side of MJT as J approaches infinity, and the entire upper half plane is in the complement. Also, wait, it's also so MJ is basically squeezed between two giant uh, balls that are tangent at some point on MJT. And that's going to be what we're going to do. So first, let's start with the easy half of that problem. Okay, so if I'm given a compact subset of the lower half plane, then there exists some, oh, okay, yeah, I'm given that, and I'm given some tau, some time less than 0. Then there exists some j such that k is a subset of omega j tau for all t greater than or equal to tau. Sorry, t. Right. So, and I kind of didn't use this notation for a while, but omega j t, that is the kind of the set that is bounded by mjt. Remember, m is compact, so all of these rescaled surfaces are compact. All of these things are compact. So this is some compact set. So this is the interior of that set. Okay, so what is it saying? It's saying that I can take any compact set in the lower half plane, and eventually this M has to be kind of above it. Oh, well, that's not quite right, but M has to be outside it. So let's prove that. Claim, I'll call this claim 1 actually, because I have another claim. Okay, so if tau is equal to 0, then I know that Hj 0, 0, that's less than or equal to J inverse, so that goes to 0 as J goes to infinity. So using my inscribed radius estimate, I know mu 0, 0, that's less than or equal to alpha inverse Hj, which goes to 0. But that implies that the inscribed radius mu inverse, which is the radius, inscribed radius, goes to infinity, right? Right, so that there is a ball of arbitrarily large radius. If I make J large enough, I can fit an arbitrarily large ball in the lower half plane in the interior of omega jt. So therefore, k is in omega j 0. Now if tau is less than 0, then because the surface is mean convex, so we're looking at mean convex, mean curvature flow. Yeah, due to mean convexity. The flow is always contracting, right? Because the surface flows in the direction of the mean curvature vector. If the mean curvature is always positive, it's always contracting. So then whenever T1 is less than or equal to T2, I have omega J T2 is contained in omega J T1, okay? Which means that K, which is contained in omega J 0, is contained in omega J tau. Right, so now I know that the M is somewhere, like as J approaches infinity, M is like somewhere in the upper half plane, or it either goes to zero or you can't have any parts in the lower half plane. So, well, now I want to show the same thing for the upper half plane, which is a lot harder to do. And this is where there's a lot of geometry and some pictures. Okay. Claim 2. So if you have a compact K in the upper half plane, and I have a tau less than 0, then there is some J such that K is in Rn plus 1 minus this. Okay, so now the problem with just doing this exact same thing is that this is not true. Like it's the exterior, this statement here is not true, so I can't do this exactly. So, and I also somehow, and so I need to somehow get a bound on the mean curvature at times less than 0. Because I can't use the mean curvature at time 0 because I don't have this containment principle here. So I need to find some way to find a bound on the mean curvature at times before 0, and then I can use the non-collapsing to find a ball that's above it, and then something like that. Okay, so let's proof. So let's fix some epsilon greater than 0 and r greater than 0. So epsilon is small, and r is very large compared to epsilon. And define the ball B r epsilon to be the ball of radius r centered at minus r plus epsilon en plus 1. Okay, so then I'll just draw that. Okay, well, okay, so here is xn plus 1 equals epsilon, and here is xn plus 1 equals 0. So what this is it's basically something like this, a ball like that, and the center is, so now if I evolve this by mean curvature flow, evolve this surface by mean curvature flow, this ball, for some time, enough time to reach this point here. This point is 0. 0. Oh, no, 0. Okay, so so I take this BR epsilon and I evolve it for some amount of time so that I just touch 0. Okay, now I know that M to 0 is an element of M0J for all J, right? Because when we define the blow up, we made it so that this was true. So I know that M intersects this point. So here's M, so it looks something like this, right? Oops, where it disappeared. And there's M. 0. MJT. So M intersects, MJ0. So M at time 0 intersects this this set here. So I'll call this BR epsilon evolved for time capital T, and this is BR epsilon. So by the avoidance principle, it has to MTJ intersects BR epsilon T for all T in minus t comma 0, right? Because if that wasn't true, if mjt did not intersect bi epsilon t for some time in the past, then it wouldn't, then by the avoidance principle, it would not intersect any time in the future, and so this couldn't pass through 0 here. Okay, so b epsilon is not contained inside omega tj for any t in minus t comma 0. Okay, so now let's fix some tau in minus t. Okay, actually, I should say that if you do kind of like a calculation, if you solve mean curvature flow in a ball, then this capital T, that's equal to epsilon squared plus 2 epsilon r divided by 2n. The point is that if epsilon is small and r, I can make it large. So this capital T can be made as far in the past as I want, so long as it's for whatever up to minus j, right? So this, by taking j large or t or r large, this tau can be as small as negative as I want. Yeah, so fix tau in minus t 0. Okay, so now yeah, I'll draw on this thing again. So I know that if I draw any compact set of the lower half space, I can take j large enough so that mt does not contain this. This is contained completely in omega j tau, right? So that means that there exists some epsilon j less than epsilon. It could be negative, such that the ball br epsilon j is touches. Okay, well, br epsilon j is completely contained in the interior of jt and tau, and partial br epsilon j intersects. So I have some point a pj in this intersection with m tau j. So I mean, that's kind of maybe a bit confusing, but so what I have is I need to draw another picture. So I have here is mjt. Here is, let's say, here is 0. mjt could go negative, so I'll draw like this. Here is xn plus 1 equals 0. Now any compact set in the low half space I can take j large enough so that I can get out of that. So what I do is I draw a really big circle far below m, make j large enough so that that doesn't touch m, and then make it a ball of radius r, and then just move it up until it touches m for the first time, right? So I guess I can just do this, can't I? Yeah, move it up, and it just touches m at one point, right, like that. And then this is the point minus r plus epsilon j. Well, en plus 1. Okay, so that's how I find this point. Okay, so that's good because I have a ball that's tangent to mj tau, tau. And so that gives me a bound on the mean curvature at that point. Right, so if I have a ball on the interior, then that immediately tells me the smallest principal curvature, the largest principal curvature is bounded by n times whatever the radius, whatever the principal curvature of the ball is. So I know that h, j, pj, so this pj is this point here, comma tau is bounded by n divided by r. So, and also make j large enough so that the p is the n plus 1 component of p, We can make it as small as we want. Oh, sorry, it's yeah, so it's greater than some minus delta, where delta is greater than 0. Sorry, so you pick some, yeah, so you can make it as small as we want by taking, based on this claim that I used, the claim 1, I can make it pj as bound its an en plus 1 component in the negative direction. So let's compute how far away pj is. Okay, I need to draw another diagram. There's this, so I have here is my here is, okay, so I have minus, here is minus delta, here is 0, and here is d, and here is m tau. M tau just touches there, m tau j. So here's pj, and here is 0. Okay, so and this thing here, that's b r epsilon j. So well, I have this bound minus delta. So the furthest away that pj could be is this point here, right? So this is just some Euclidean geometry. We have this triangle here. We want to find out how far away this is from this point here. So we can just calculate that. Pj therefore has to be less than or equal to so delta squared plus so this height here, this is r minus epsilon plus delta. This height here from this height here, from here, and so this is square root of r squared minus r minus epsilon plus delta squared. So then this distance here, the maximum distance is going to be delta squared plus r squared minus r minus epsilon plus delta squared. So that's equal to square root of 2r epsilon plus delta minus 2 epsilon delta minus epsilon squared. No, that's not quite right. 2.
There's an R missing in the epsilon delta.
Yes.
Yeah.
Epsilon delta r.
Yeah.
Right.
All right.
Okay, so yeah, okay. So then all right, so then I want to, okay, just to simplify this, wait, should this be a plus? No. Okay,
And
so
also a delta squared missing, maybe?
maybe I think this is, oh yeah, there's, let's see. So delta squared plus
Oh, no,
r.
the delta squared cancels with the other delta squared, and then
Yeah. Anyway, so either way, I'm going to set delta is equal to something that makes this last part equal to 0. So it's going to be plus, right? No, it's written down minus. Anyway, and delta is equal to minus, wait, no, delta is positive. So it should be 2 epsilon. No. Well, I've written down the answer. Either way, it's okay. There it is. Okay. So it's 2 epsilon squared on 2r. But that doesn't, that doesn't seem
doesn't
to,
look right.
maybe that's, I'm just trying to figure out what, based on the answer, I'm trying to figure out what it should have been. So yeah, then looks like this should be a plus then. Yeah, this should be a plus. Okay. Well, okay. Anyway, either way, if I set this as this, then I get 2r epsilon plus delta. Yeah.
Yeah.
Okay. So I mean, I haven't. So now I want to also use this non-collapsing. So I know that the mean curvature is bounded by n on r. That means I have an inscribed ball of radius alpha r divided by n. Okay, so there is the ball. Okay, so if I take the ball, b r alpha divided by n qj, that is contained in Rn plus 1 minus j tau. Where this point qj, so over here, here's the normal vector. That's nu j pj comma tau. Oops. The x squared ball is going to be, the q is going to be in that direction, r alpha on n. So it's equal to pj plus r alpha on n nu j pj comma tau. Okay, so this wouldn't be very useful if this nu j was like sideways, was pointing sideways, because then I'm not getting compact sets in the upper half plane anymore. I'm only getting compact sets of some strange kind of set, right? Which is anyway, so I want this nu j as j approaches infinity to hopefully be pointing in the en plus 1 direction. That's easy to show. Let's compute nu j pj comma tau in the en plus 1 direction. That's rearranging this. I get pj en plus 1 minus let's just, well, okay, yeah, let's do one more step. So nu j pj comma tau equals q is equal to pj minus epsilon j minus r. Where is this coming from? Oh, right. I see. So this nu j has the same normal vector as this big br epsilon j, right? So I know where the center of br epsilon j is, so I just need to go and look in that direction. So to find out what this is, so it's this point, go in that direction, right? So it's this, so it's pj minus this made into a unit vector, right? So that's equal to this divided by en plus 1 divided by r. Move this down a bit. And so I get pj comma en plus 1 minus epsilon j minus r divided by r, which is equal to 1 plus pj en plus 1 minus epsilon j on r. But I also know that this thing is bounded below by minus delta, right? I can make pj as high as I want. So that's greater than or equal to 1 plus delta plus epsilon divided by r. Okay, that's good because r can be made large and epsilon can be made small, and delta becomes small as r becomes large, right? Right? So all good. The nu j is becoming closer and closer to being in the en plus 1 direction. Okay, so using all this, we're going to try and bound the height of this, of mj tau, right? We want to bound this height. So I'll draw another picture. Okay, so here is mj tau, and here is 0. Okay, I don't want to. Okay, so here's 0. Actually, I don't really need to draw 0. So here's PJ. And here is that exterior ball. And, oh, actually, so here is, let's say a 0 is over here, the point 0. And then I also know that PJ lies within this set. Oops, keeping. Okay. That's this set here. That's the ball of radius square root of 2r. What was it? R minus delta at 0. So MJ tau lies on below this set here, this line here, and I know that PJ lies within this set here. So the maximum values are going to be at these at this intersection. The maximum value of so MJ is going to be bounded below these 2 points at least. Okay, so in order to estimate the height, I need to estimate the height of these 2 points here. Okay, so let's take some point Z. Well, there's not. I say 2 points. There's a circle of points. I mean, there's a sphere of points. So let's take Z in this set. So Z in partial B square root of 2r minus delta 0 intersect partial B r on n alpha qj. Okay, so let's see. The distance from Z, so here's qj, all the way up there. The distance from Z to qj is equal to r divided by alpha, r alpha divided by, so Z, so r alpha divided by n squared is equal to Z minus, so I'm trying to estimate, so I want to estimate this thing, Z comma en plus 1. So this is Z minus qj squared. This is, let's see how much, so I'll do this, go do half of this calculation. I'll do some parts of it and then I'll move on to the next part of the proof. So here we get Z minus qj en plus 1 squared plus some, I'm just decomposing it into components, k equals 1 to n of Z minus qj ek squared. And that gives me minus 2 Z en plus 1. So expanding this, qj en plus 1 minus 2 k equals 1 to n of Z comma ek qj comma ek, and then combining parts from this and this, I get Z squared plus qj squared. So I can rearrange this to get Z en plus 1 is equal to Z squared plus qj squared minus 2 sum k equals 1 to n Z comma ek qj comma ek minus r on n alpha squared divided by 2 qj en plus 1. Okay, so then, well, Z squared, the length of Z, that's equal to 2 epsilon r minus delta, right? And then, so let's see. So, yeah, maybe I will leave. I'll not do the rest of this calculation. So you can kind of maybe be convinced that this is you can bound this quantity by just let me just look at the individual quantities, right? So okay, so z I get, so for the z part I get that's equal to 2 epsilon r minus delta, okay, and then the QJ in a product with EK. So QJ is what it, so QJ was this thing here. You go to PJ and then you go in the normal vector QJ amount. But I kind of showed that if nu J, as J becomes very large, this nu J, it's the same direction as En plus 1. So this QJ is directly above 0. So you expect, like you do some calculations and you saw that all these terms actually go to 0. Okay? Now, what about the norm of QJ squared? Well, that is going to be proportional to R. It's going to be, well, I have it here, don't I? Where is it? Yeah, norm of QJ squared is going to have an R alpha on N squared. So we'll cancel out with that term. And then it will just have a PJ inner product with this thing here, right? And that I can make as small as possible, right? Because it's the EK component, because this approaches En plus 1, and this I can make very close to 0. So then that part doesn't have much influence. And then I have QJ En plus 1, and that's very large because this ball is becoming very large. So maybe I can leave it as an exercise to do the rest of this actual calculation, but it's hopefully that rough explanation says why you expect this to be as small as possible as J, can be made as small as possible as J becomes very large, right? Maybe I can say what the estimate is. So yeah, so this turns out step less than or equal to some constant alpha inverse epsilon. Yeah. Okay. So that finishes the proof of the claim, because now I've shown that the height is low on very large balls as R approaches infinity. This ball, this ball becomes everything, it gets very large. So I'm bounding it in larger and larger sets. So that proves the claim. Any questions about that? Okay, so now now that just says that as you just get these metric spaces, these surfaces of metric spaces are approaching the xn plus 1 equals 0 plane. We need to prove that the convergence is smooth. And for this, I'm going to use this theorem, the Brachy-White theorem. It says that there is an epsilon greater than 0 such that if this quantity, I'll say a bit about it, sup p x0 t0 of 4 pi r squared to the minus n on 2 mt minus r squared e to the minus x x0 squared divided by 4r squared. That's less than or equal to 1 plus epsilon, then the curvature is bounded in a smaller ball. So what is this? So actually, the proof of this theorem is very similar to what I've said so far. Assume this isn't true. So put take a sequence of, there exists a sequence of counterexamples where this quantity is less than or equal to 1 plus J inverse, right? And then over here you show, but there exists a J, but the supremum of A is greater than or equal to J. you blow up just as this is kind of like we've done in this proof, and then you show that the limit converges to a static hyperplane, and then you contradict this statement here, okay? Because the limit actually, as you go to infinity, this quantity here, that's going to go to 1. The limit will satisfy Gaussian density is equal to 1, and there's only one solution. I mean, there's only one surface that has Gaussian density equal to 1, and that's the static hyperplane. Also, sorry, I didn't mention that this thing is called the Gaussian density. So it kind of says that if the mean curvature flow kind of at all scales looks like is very close to the mean curvature flow of a static hyperplane, then the surface is actually in C infinity close to a static hyperplane. So actually, I don't need to compute this integral or anything. I can, if you look at the integral, you can see that actually it doesn't depend on anything about the surface except for the measure on the surface, right? If I have a family of surfaces, only thing that I need to think about is the measure on the surface, and then this integral here, that is a function on the surface, but it's just the measure, which is like I guess the support of, well, okay. Yeah, so I only need to prove that the measure converges of this sequence MJT converges to the measure of a static hyperplane, right? And so I just need to show that so what do I need to show? That MJT intersect ERX. So if it was a static hyperplane, then I could make J very large, and so this would just be the area of the n sphere, omega n r to the n, but it's not going to be true for any. It's only going to be true in the limit, so I just need to show that there exists a J so that this is true. Right? There's some J large enough so that I can make the area of MJT intersect with this ball equal to this, less than or equal to that quantity. So yeah, for all epsilon greater than 0, there exists J such that this is true. Okay, let's do that in 2 minutes. Okay, so let's fix some tau in minus J comma 0, and let K be any compact set. Compact domain such that, oh sorry, not compact, closed, such that K agrees with omega JT outside ERX. So I have like, here's your omega T, omega JT, and here is the ball, and here is K, something like that. So this is, so K is this part. This is K, and omega is this part. Then this quantity, the area of K in this set here, minus well, okay, so it's minus the area of MJT intersect BRX is less than or equal to, oh sorry, it's greater than or equal to 0. So MJT actually kind of minimizes this, is always has lower area in this set here. Okay. So okay, so you can think of omega jt for past times as kind of, it goes through this set like this, like that, so like that. And at each point, you have a normal vector field. And so we can write this area down as that's equal to the integral on partial k intersect brx of, so it's equal to the normal vector field. So this is a normal vector field on this region here in between these two sets, times this restricted to partial k. This is just on the boundary, minus the integral on mjt, same thing, brx. I mean, normal vector is equal to 1, so this is why this is the same. Restricted to mjt, yep, tau. But then I can integrate that in the interior to get, that's in k minus omega jt intersect brx of the divergence of this vector field. But the divergence of the normal vector field is always just equal to the mean curvature of this family of surfaces which is evolving under mean curvature flow. Oops, I've gone over time. H greater than or equal to 0. Okay, so sorry, I had to rush that end there. But I'll just say that apparently, if you set k equals omega jt union brx intersect xn plus 1 is less than epsilon, that gives you that using k to be setting k to be that, it gives you that partial k intersect brx. Sorry, it gives you partial. It gives you mjt intersect brx less than or equal to 1 plus epsilon omega n r to the n. But I couldn't verify that. I tried to, but it didn't look right to me anyway. So sorry, I went over time.
It's okay. No worries. Thank you, Vishnu, for your presentation. So I'll just clap on Zoom. It's a bit strange, but I'll clap on Zoom. Okay, do we have any questions for... I'll stop the recording now, and then we can do questions